A new hypothesis suggests that our universe could be twice as old as previously estimated. However, this is still not the final accurate information, as no scientist has yet been able to definitively confirm the true age of the universe. The initial cosmic observations obtained from the ZX Space Telescope do not align with the current cosmological models in use. This model estimates the universe to be approximately 13.8 billion years old, based on the hypothesis of cosmic expansion following the Big Bang. The study conducted by Professor Gupta from the Department of Physics at the University of Ottawa proposed a new model, which redefines the age of the universe as 26.7 billion years. To explain observations of the early universe, which cannot be achieved with the Webb Space Telescope, primitive galaxies could not exist. In reality, some galaxies had already formed at the dawn of the universe, roughly 500 to 800 million years after the Big Bang. There are disks and bulges similar to galaxies that have undergone long-term evolution. And smaller celestial bodies appear to be heavier than larger ones, which completely contradicts what we typically think. The age of the universe is estimated based on its rate of expansion. By measuring the redshift of spectral lines in the light emitted from distant galaxies. The redshift phenomenon of light is similar to the Doppler effect in sound. When a sound source approaches, we hear a higher frequency, and when it moves away, the perceived frequency is lower. The redshift phenomenon occurs when the frequency of light decreases, indicating that the object is moving away from us. As galaxies move farther apart, their recession velocity increases, leading to a greater redshift effect. Another explanation for the phenomenon of redshift is the Doppler effect. Distant galaxies are moving away from us at a speed proportional to their distance, which proves the universe is still expanding. Most astronomers support the expanding universe model. Two astronomers, Arno Penzias and Robert Wilson, while working at Bell Labs, accidentally discovered the cosmic microwave background radiation. In 1964, the cosmic microwave background, CMB, could not be adequately explained by the steady-state model. The expansion rate of the universe is essentially the key factor determining its age. When the Hubble Space Telescope was launched in the 1990s, although the exact rate of expansion cannot be determined, the age of the universe is estimated to be between 7 and 20 billion years. Determining the age of the universe is a fascinating scientific challenge, and currently, researchers primarily use two main methods to address this question. The first method is to measure the expansion rate of the universe, as mentioned above. The second method is to observe the brightest stars. Just like estimating the age of a tree by counting its rings. Scientists can study the chemical composition and internal structure of the oldest stars in the globular clusters of the Milky Way. Globular clusters can contain up to 1 million stars, and it appears that all of them were born around the same time during the universe's early stages. Suppose all galaxies and star clusters began forming at the same time. The age of the oldest star in the cluster will reveal the age of the universe. Currently, the oldest stars ever studied indicate that the universe is approximately 13.6 billion years old. Both methods have their limitations and areas of uncertainty. Studying old stars requires relying on complex stellar models and analyzing their distinctive chemical signatures. Measuring a large number of spectral data points related to analyzing distant galaxies with high precision can be a significant challenge. However, by combining these methods and considering additional observations, such as cosmic microwave background radiation, we can achieve more accurate results. Scientists have collectively estimated that the universe is approximately 13.78 billion years old. However, is the universe truly older than we think? According to GameWeb, we may need to reconsider how we interpret ancient stars or certain numerical sequences, as they could lead to overestimating their actual age. A study published last year proposed a solution to the problem of primordial galaxies, previously thought impossible to exist, by applying the tired light model. However, the phenomenon of tired light cannot adequately explain other cosmic observations, such as the redshift of supernovae or the uniformity of the cosmic microwave background. Professor Gupta has worked to integrate the standard Big Bang model with the tired light theory to assess their compatibility with data from supernovae and information gathered by the GameWeb Space Telescope. This model pushes the age of the universe to 19.3 billion years. Next, Professor Gupta experimented with constructing a model that combined tired light with an expanding universe model based on the evolving coupling constant, a theory proposed by British physicist Paul Dirac in 1937. This result aligns with both data sources and nearly doubles the age of the universe. The new model extends the universe's formation phase by 10 to 20 times compared to the standard model, thereby providing sufficient conditions for primordial particles, previously thought to be unsustainable, to fully develop, aligning with actual observations. Combining two models to explain newly observed phenomena is not a novel method. Isaac Newton proposed that light travels as particles in his theory. This theory dominated until the 19th century, when it was replaced by the wave theory of light, which could explain observed diffraction phenomena when using monochromatic light. Albert Einstein restored the particle nature of light to explain the photoelectric effect. Light has a dual nature, meaning that in different experiments, it exhibits both particle-like and wave-like properties. From then on, scientists have discovered evidence proving that particles of matter also possess wave-like properties. For example, in the electron diffraction experiment, electrons demonstrated wave-like properties by producing interference patterns on the screen. Additionally, in the double-slit experiment, electrons also exhibit particle-like properties when passing through individual slits, depending on their position. Although some observations from the Hubble Space Telescope have suggested that the early galaxy could not exist. But it wasn't until the Webb Space Telescope was launched in December 2021 and began providing data by mid-2022 that this issue was conclusively confirmed. Therefore, the scientific community is gradually moving toward a new physics to explain observations from the Webb Telescope. At just 26.7 billion years old, it will undoubtedly completely transform humanity's understanding of cosmic history. However, this does not mean denying the fundamental principles of the Big Bang Theory. Instead, it may require us to adjust and upgrade existing models, while also opening up the possibility of exploring new, previously unknown physics concepts. This is a clear illustration of how scientific progress operates in practice. The remarkable discoveries from the Webb Space Telescope have truly accelerated the journey to unravel the deepest mysteries of the universe. Moreover, this is only the first step. In the coming decades, thanks to increasingly advanced generations of new telescopes, we will uncover many more fascinating things about the universe. No matter the outcome, the discoveries from the Webb Space Telescope will undoubtedly continue to expand humanity's understanding of the universe for many years to come. From the moment of its inception, Webb has ushered in a new era in the field of space research. Regarded as the divine eye and the pinnacle of human technology, in the future, it may lead us to incredibly wondrous discoveries. Thank you all for watching this interesting video.